Process of discussing the basics of particle acceleration and particle detection methods. In this video we will demonstrate how photons interact with matter. At the end of this video you will know the mechanisms by which they are detected, namely the photoelectric effect, Compton scattering and pair production. In these processes the photon is either absorbed or scattered by a wide angle. Most of the photons in a beam keep their original energy, but their flux is diminished. A photon beam will thus be attenuated rather than lose energy. The probability of an interaction in a given target thickness is a constant proportional to the cross-section of the process. This leads to an exponential decrease of the intensity of a photon beam as a function of absorber thickness. We have already calculated an example of this in the optional video 1.3a. Photons are detected by interactions which produce charged particles. The photoelectric effect is the absorption of a photon by an atomic electron dominant between the ionization energy of an atom and about 100 keV of photon energy. Compton scattering is the elastic scattering of a photon of a quasi-free atomic electron dominant around photon energies roughly 1 MeV. Pair production is the conversion of a photon into an electron-positron pair in the electromagnetic field typically of a nucleus, dominant for photon energies much larger than 1 MeV. We will discuss these processes one by one in what follows. In a photoelectric process, an atomic electron is released when the atom absorbs the photon. Its kinetic energy is then the difference between the photon energy and the ionization energy. This latter one depends on the shell where the electron was and is typically between 1 and 25 electron volts. The photoelectric process is not feasible for a free electron. It would violate conservation of momentum. If the photon energy is larger than the K-shell energy, the cross-section is dominated at the level of roughly 80% by the absorption of K-shell electrons, since the proximity of the nucleus eases the absorption of the recoil energy. Sigma Th in this formula is the standard cross-section of Thomson scattering. It sets the scale of this cross-section. The dependence on the atomic charge to the 5th power and the photon energy to the power -7/2 favors the photoelectric process for low-energy photons in heavy materials. At high energies, in the relativistic limit, the energy dependence becomes simply 1/E gamma. The vacancy opened by the photoelectric effect can be filled by another electron of an upper shell, say the L shell for example. This will result in either the emission of an X-ray with energy EL minus EK, or the emission of an Auger electron if the available energy is greater than the ionization energy for higher shells. In Compton scattering, dominant at intermediate energies around 1 MeV, a photon is scattered off a quasi-free electron. The cross-section is given by the Klein-Nishina formula, which is obtained by quantum electrodynamics that we will discuss in Module 4. The energy of the scattered electron is maximum when the scattering angle is 90 degrees, with a maximum electron energy that is given by the formula on the bottom of this page. The Compton scattering cross-section is typically about 0.1 barn in the forward direction. For backward scattering, it varies between 0.1 barn at low energies and 0.04 barn at 100 keV. At high energy, the process is thus dominated by scattering in the forward direction. In the electromagnetic field of a nucleus, the photon can convert into an electron-positron pair. The energy threshold is essentially twice the mass of the electron, with a small correction for the mass of the recoil of the nucleus. This process cannot take place in vacuum because of energy momentum conservation, but little energy is transmitted to the nucleus, about 1 MeV for heavy nuclei. At low and modest energies, the cross-section per atom is given in terms of the radiation length. This is the same length as the one we defined in video 3.5, i.e. the length after which an electron loses all but 1/e of its energy by Bremsstrahlung. In this image, taken with a historical bubble chamber, we see the tracks left by charged particles as small bubbles formed in an overheated liquid. The chamber is immersed in a magnetic field orthogonal to the projection plane, which deflects the trajectories. This is an atypical process in that a photon enters from the left and converts into an electron-positron pair in the field of an atomic electron and not in the field of a nucleus. This produces what is called a trident. These are the three charged particle tracks you see attached to the left vertex. The pair particles lose their energy in the liquid. Their trajectories are the spirals that you see on the left. The atomic electron takes an appreciable recoil energy because of its small mass. Its stiff track goes to the right with very little curvature. About halfway, the electron emits a Bremsstrahlung photon, which in turn converts into an electron-positron pair. You see this pair by the V-shaped tracks on the right. The cross-section for pair production becomes almost independent of the photon energy above an energy of about 1 GeV, and then depends only on the material, that is to say, on x0. The conversion probability per unit distance is inversely proportional to the radiation length. The mean free path for a photon before it converts is the inverse of this probability, and thus 9/7 of a radiation length. The busy plot on the right shows a summary of the contributions of all processes to the photon total cross-section in matter. Among these, the most important ones are the photoelectric effect at low energies and pair production at high energies. In between, around 1 MeV, at the minimum of the cross-section, Compton scattering dominates over other processes. At high energy, as we have seen, at energies above 1 GeV, electrons and positrons lose their energy almost exclusively by Bremsstrahlung. Photons convert to electrons and positrons by pair production. The two phenomena have the same characteristic length, the radiation length. The successive combination of these two effects results in the formation of what is called an electromagnetic shower. Whenever an electron, positron or photon of high energy enters into a medium, it will cause such a shower. A simulation is shown on the right. Again, each black dot corresponds to a unit of energy loss. In the next video, we will see how ionization detectors measure the passage of charged particles.